In the world hidden behind your light switch, people work night and day to bring electric power to you. Bonneville Power Administration, an agency of the Department of the Interior, is part of this world. Bonneville Power Administration is people and the tools and materials they work with. People who work with conductor as big around as a man's arm. People who build the towers to carry rivers of power. People who operate the biggest high-voltage grid in the nation. Who plan the system, maintain it, work in the air, on the ground, even beneath the sea. Our story begins at the dams. There are nearly 30 federal dams in the Columbia River Basin. BPA markets power from all of them. This is Grand Coulee, the biggest. BPA doesn't build or operate the dams. The Corps of Engineers and the Bureau of Reclamation do that. Those transmission lines, that's our story. We take over here and cross mountains, plains, and rivers, carrying power to substations, where utilities who buy their wholesale power from us take delivery and distribute it to you for 1,000 uses. Bonneville serves large industries direct, including 30% of the nation's aluminum capacity. Altogether, we supply half the electric needs of the Pacific Northwest, and at the lowest wholesale rates in the nation. To do this, we've built 10,000 miles of transmission lines, reaching from the Continental Divide in Montana and Wyoming to the shores of the Pacific Ocean, and from the Canadian border, that swath down there that looks like a right-of-way, clear to California. Heading south from the Columbia, a new breed of towers is going up, carrying 500,000 volt alternating current, 750,000 volt direct current lines. Electrical freeways to sell and exchange power with California, Nevada, and Arizona. It's called the Pacific Northwest, Pacific Southwest Intertie. Behind your light switch stands not just your utility, but every major utility in the Northwest and British Columbia. And soon, through the Intertie, every utility on the West Coast will be interconnected in a giant power grid. From California to Canada, from the Continental Divide to the Pacific Ocean, the strongly interconnected Bonneville grid is there behind your light switch. Thus, the symbol for BPA is not a dam, but a transmission line. Every inch of the 10,000 miles is engineered to do the job with reliability and economy. BPA, since its inception, has been a leader in transmission technology. Its high-voltage grid is world famous. With research instruments like this, BPA engineers are able to set up regional power systems in miniature and study the complexities of power flow. They work on the frontiers of technological change. Federal power in the Northwest didn't begin with Bonneville Power. This line in Idaho was authorized by Teddy Roosevelt and was built in 1903. BPA, established in 1937, didn't come to southern Idaho until 1963. That area presents some interesting problems for which we have some interesting solutions. This mobile substation is one of them. Growing loads strain an antique power system. With this mobile substation, we can move into a critical situation and bring the voltage up to where it should be. Not all our transformers move along the highway with the speed and ease of the one in Idaho. Some of them are as big as a house and somewhat heavier. Once there, they stay put. We design and build the substations too. Install the equipment, transformers, circuit breakers, power system control devices. We've built and operate more than 250 substations. These are the distribution points for one of the strangest products in the world, electric power. It is produced, delivered, and consumed all in the same instant. You can't store electricity, but you can store the water to produce it. We control this powerful force with our fingertips, hundreds of miles away in the Bonneville Control Center in Portland. At this center, every mile of line, every substation, every key switch on the BPA system is controlled or coordinated. The power dispatcher is the key man. No switch on the BPA system is touched without his knowledge and approval. He has to anticipate the constantly changing power needs of 6 million people and exactly match generation to demand. He balances generation and demand with split-second accuracy. That second is split into 60ths, not halves or quarters, but 60ths. If generation and demand get out of balance, the whole power grid can break up and result in a blackout like the one in the Northeast in November 1965. In that case, millions of people went without power up to 12 hours. Our Northwest grid has fallen apart only once, in 1950, and it took less than an hour to put it back together. Our grid is less vulnerable to blackout and easier to put back together. One reason, we have an all-hydro system. Dams respond instantly to changes in demand. Another reason, we are strongly interconnected. Third, and very important, BPA serves large industrial loads which can be dropped automatically without economic disaster to help prevent a system breakup and, should one occur, to make easier the dispatcher's job of matching generation and load to put the system back together. The dispatcher's chief responsibility is to keep generation and loads in balance. He has help from power schedulers who draw on years of power use patterns to set minimum levels of power production at all dams to meet anticipated requirements. He has more help from these two sophisticated computers, conceived by Bonneville engineers. This one measures actual demand against anticipated demand. At 7:06 a.m., when yours and 200,000 other toasters go on, the needle goes this way, and the change in power demand of the entire region is computed instantly. At that instant, this computer sends the new power requirements to the other. It is tied to 5 federal dams, which carry the swings in load. It tells each of the dams how much power to generate at any given moment. Flick your light switch at any hour, day or night, and the right amount of power is there. This computer controls not only the flow of electricity, but also the flow of water to get the most kilowatts as it passes through all the dams on the river, within limits set by the Corps of Engineers for navigation and flood control, and the Bureau of Reclamation for irrigation. The control center contains a maze of telemetering instruments and techniques. There is even an instrument that records the amount of ice on a line 300 miles away. Telemetering may tell you something is wrong, but it can't go out and fix it. That takes men. In winter, you get there the best way you can. You go as far as a 4-wheel drive and winch will take you. If that won't make it, you take a snowcat. If that won't make it, well, there's always this way to get up a mountain. At Mount Spokane, there is this way, too. That's the easy way. There are all kinds of trouble on a big power system, short of a blackout. Some large, some small. Trouble in complex electronic equipment is usually minor, but hidden. The main job is to find it. When major trouble comes along, you don't have to look. It will find you. 5:19 a.m. Trouble has just announced itself at Big Eddy's substation. 100 miles away, at the same instant, it arrives here too. The Big Eddy Midway line is dead. The operator tests the line by re-energizing it. It kicks right back off. No doubt, the line is out.
Hello, dispatcher. This is Brown at Big Eddy. Looks like we have major trouble on the Big Eddy Midway line.
For the dispatcher, this is indeed real trouble. The line connects Grand Coulee with the Dalles Dam. Other lines will carry the power, so no customer service is interrupted. But this outage places the system in jeopardy. The loss of another line between Coulee and the Dalles could black out customers. He alerts line crews at both ends. Meanwhile, radar-like blips on a fault locator screen pinpoint the trouble 52 miles south of Midway. This is the scene 52 miles out. Freezing fog has built up enough ice to mangle a tower. All the resources of BPA's Walla Walla area go to work to put this critical line back in service. Conductor has to be cut free by torch from the twisted steel. A temporary bypass is built on a wooden pole. It's called a shoe fly. The damaged conductor is repaired with armor rod. Conductor is strung to the shoe fly. Crews work round the clock in freezing temperatures. The line is restored in 20 hours. Not one light in the Bonneville service area even dims because of this outage. Outages like this, though not headline makers, are bound to happen when you operate 10,000 miles of transmission lines exposed to the elements. Happily, we manage to make most of them our problems and not problems for our customers. The best way to overcome major trouble is to avoid it by spotting it while it's a minor flaw. This is how we do it. An experienced lineman travels along as observer, 50 miles an hour, 25 feet above 250,000 volts. 5 towers to the mile. Time to note whether the section is good or faulty. Five towers to the mile and 10,000 miles to go. 10,000 miles covers a lot of territory. Arid land, marshy land, and rich land. It follows a geography all its own. Burnt woods to Toledo, potholes to Pelican Horn, Nellie's Corner to Lone Pine, Fern Ridge to Fox Hollow, 50 miles an hour, 5 towers to the mile. The observer notes any flaw that catches his eye. He sees a flashed over insulator. This is how it got that way. The moment lightning strikes, relays respond. Open the circuit breakers. Allow the lightning flash to go to ground over a dead line. Automatically, the line comes back to life. All this in a fraction of a second. The burned insulator must be replaced. We can usually protect the system against the wrath of God, but not against the foolishness of man. It costs us $30,000 a year to replace insulators shot out over the system. It could cost the misguided marksman his life if the line should drop near him. If we had to de-energize a line every time we changed an insulator, every day some customers would go without power. We do a lot of our maintenance with the lines energized. We call it hot stick work. How would you like to touch 250,000 volts with a 10-foot pole? It is part of a day's work for these men. They do it at a scientifically calculated distance from instant death by electrocution, 10 stories above ground. At times, it is impossible to repair a line without de-energizing it. Even when a line is dead, the work can be dangerous out there on a bosun's chair. This routine maintenance calls for armor rod to repair the conductor without lowering it to the ground. Sometimes a segment of the line has to be replaced. This one because of gunfire again, the work of a vandal. For this particular job, it takes 10 men, 16 hours to repair the damage done in a careless moment. The right-of-way itself needs attention. Access roads have to be cleared of brush. Lines have to be kept free of trees. This is our answer for brush control. It is affectionately called the Monster. The Monster is a converted tank destroyer from World War II. Old soldiers never die, but a 20-year-old tank destroyer is about ready to. We are looking for new ways to keep the right-of-ways clear. So we have taken to the air. This spraying must be, and is, done without damage to fish or wildlife or adjacent forest or property. It is hard to draw a line between emergency and routine maintenance. We have to be organized to correct trouble when it happens, where it happens, no matter what the cause. Water, our friend, the source for our electricity, can go wild and turn against us. It can wash out the footings of a tower. Yet this emergency too is treated by routine techniques. We wait until Sunday to build our shoe fly. No customer service is interrupted. Transmission lines are not our only vulnerable equipment. Water on a rampage can tear up a switch yard. We couldn't wait until Sunday to take care of this. Emergency repairs hold the ground. Routine switching to auxiliary equipment provides uninterrupted service. Just about now, we think we have built the best system in the world and learned how to maintain it without serious customer interruptions. And then it happens. The San Juan cable is dead. This is a big one, the worst we've had in a long time. Millions of people are not involved, but 6,000 are. And although we don't know it at the time, they are going to be on ration power for 3 weeks. The dispatcher can work no magic. He has no alternative routes to the 4 miles of submarine cable connecting the islands with BPA's mainland grid. Old standby diesel generators that haven't had to work for 13 years are pressed into service. They can carry but 1/3 of the power load today. The islanders have to use their own standby units. Within 24 hours after the cable break, BPA has this trailer unit from BC Hydro in service. Next, we locate and tow in a floating diesel unit from New Westminster, BC. Other units follow. Over a weekend, BPA builds a complete substation to integrate the diesel generation into the island system. Meanwhile, we search for the break. BPA engineers fix their sights on this boat keeping course over the cable. A second bearing enables our engineers to chart the boat's position. This simple device, a sensing coil, built on the spot with spare parts for less than $25, enables the boat to trace the cable's broken path. A meter registers every time the coil passes over the cable. The result? An accurate plot of how the cable ends lie 50 fathoms down. Or is it accurate? There's only one way to find out. Move in barges and send down your diver. He can stay only 20 minutes at a time, 300 feet down in icy darkness. The cable had better be where we think it is. It is. Later, the diver tells us he couldn't find it at first. He was standing on it. Down go the lifting bridles. The diver is ready to come up. It took him 3 minutes to descend. It takes an hour to come up if he's to avoid the bends. Now, regular Bonneville linemen take over. The winch has lifted the cable from the bottom, but it takes manpower to horse it onto deck. Careful, almost a bath. Next day, the other end comes up. We're ready for the new cable. For 13 years, BPA has stored 2,000 feet of spare cable for just such an emergency. This job takes nearly half of it. 24 hours of round-the-clock splicing work rejoins the cable. The pressure on the men is almost as great as the pressure fusing the cable. The sea seems to sense its defeat and turns angry again the day the repaired cable returns to the bottom. "20 days after the break, after the longest and most difficult outage in BPA history, the relieved dispatcher marks the circuit normal. Everyone who's part of the world behind your light switch is in a better mood when the system is back to normal. The utility that serves you, public or private, fights the same kind of battle to bring power to you. Ice can crush towers. Water can wash foundations away. Wind, time, and tide can exact their toll. Any of our massive hardware is subject to failure under stress. It takes people to put it back together, to keep it running. To make sure the power's there when you flick your light switch.